Okay, I have to be honest. When I first opened the file for today's deep dive, I actually thought I had the wrong document.
Chuckles.
Yeah, I can see that. I thought I was looking at a schematic for, I don't know, a nuclear reactor or maybe the wiring diagram for a
Yeah,
spaceship.
it is definitely dense.
Dense is an understatement. It looks like a bowl of alphabet soup just exploded all over a circuit board. We've got boxes labeled AMF, SMF, UPF, SEPP.
All the acronyms.
Yeah, and they're all connected by these, bus lines and dotted lines. It is intimidating.
Yeah.
But you promised me that this image, this figure 4.2.41 from the 3GPP specs, is actually the key to understanding something we all use every single day.
It is. I know it looks like engineering hieroglyphics right now.
Yeah.
But that diagram is actually a map. It's the blueprint for how the entire world, stays connected when you travel.
That is a very big claim for a PDF full of acronyms.
Well, think about it. You land in Tokyo or Paris or New York. You turn off airplane mode.
Yeah.
And within seconds, your phone just works. You can watch a 4K YouTube video, check your email, map your route to the hotel. This diagram explains exactly how that miracle happens. It's the roaming 5G system architecture, and specifically it's about a concept called local breakout.
Local breakout. It sounds like a prison escape movie.
It's actually much more exciting than a prison break, at least for network engineers. It's the reason your internet doesn't crawl at a snail's pace when you travel.
Okay, so our mission today is to decode this map. We're going to turn this alphabet soup into an actual story. And I think the best place to start is just orienting ourselves. Because when I look at this, the first thing that jumps out is that vertical dotted line right down the middle.
Yes.
It slices the whole image in half.
That line is probably the most important border in the telecom world. It splits the diagram into two distinct territories. On the left side, you have the VPLMN.
The VPLMN, which stands for?
Visited Public Land Mobile Network.
Okay, let's just call it the visited network. Makes sense.
Exactly. That's where you physically are. So if you're a student from Taiwan traveling to Japan for vacation, the left side of that diagram is Japan. It's the network your phone is actually touching, the towers, the cables, the hardware in Tokyo.
And on the right side of that dotted line, we have the HPLMN, the Home Public Land Mobile Network.
Right. That's your service provider back home. That's who sends you the bill. It's where your contract lives. So the fundamental tension of this whole diagram is you are physically on the left in the visited network.
But my identity and my money are on the right, at home.
It's a long-distance relationship.
It really is.
And the goal of this architecture is to figure out how these two massive, likely competing companies can talk to each other so fast that you don't even notice the gap.
Okay, so we've got the geography. Left is home, right is home. Now, I was reading through the notes, and there's a really clever way to break down the rest of this mess. We can view it in layers.
Yes, the three-layer approach. It's a classic way to teach 5G. If you try to memorize every single box at once, you'll just lose your mind. But if you see it as these distinct stories, it clicks.
So layer 1 was the geography we just did. Layer 2, I want to call the muscle.
The muscle. Okay, I like that.
Yeah, if you look at the very bottom of the diagram, there's a solid line connecting the phone all the way to the internet. It looks like a pipe.
That's a great analogy. In engineering terms, we call that the user plane. This is the physical highway where your actual data travels. It's your YouTube video, your Instagram photo, your email attachment. It's all the heavy stuff.
And then layer 3 is that blue line running across the top, connecting all those little floating boxes like a nervous system.
That is the control plane.
Yeah.
That's the brain. That blue line is responsible for all the decision-making. It handles questions like, who is this person? Are they allowed to be here? Did they pay their bill? How much data are they using?
So the bottom line carries the cargo, the video, and the top line carries the paperwork.
Perfectly put. And in 5G, separating the cargo from the paperwork is really the secret sauce.
All right, let's zoom in on the muscle first, that user plane at the bottom, because this is where local breakout actually happens.
It is. So if you start at the far left, you see the UE.
User equipment. My smartphone.
Right. It connects to the RAN, the radio access network.
Which is just the cell tower I can see out my hotel window in Tokyo.
Exactly. Now follow the line. From that tower, it goes to a box called UPF, the user plane function.
UPF, what is that exactly?
Think of the UPF as a high-speed, intelligent router. It's the gateway. Its only job is to take the data coming from your phone and just shove it out onto the internet. And in this diagram, the UPS connects directly to the DN.
The data network.
Which is just the internet, yeah. Or maybe a corporate network, but for our purposes, it's the internet.
Now, here's what I noticed. All of these things, the phone, the tower, the UPF, and the internet connection, they're all on the left side. They're all in the visited network.
And that is the local breakout.
Why is that special? Isn't that how it always works?
No, not at all. That's the thing. In the old days, and still in many cases today, we use something called home routing.
And how does that work?
Imagine you're in Japan. You click a link to a Japanese restaurant's website. With home routing, that request goes from your phone to the Japanese tower. Then it gets put in a special tunnel and sent all the way back to Taiwan.
Wait, really? It goes home first?
It goes all the way home to your carrier in Taiwan. It exits to the internet in Taiwan. It then finds the Japanese restaurant's website server, which is probably in Tokyo, grabs the data, brings it back to Taiwan, puts it back in the tunnel, and sends it all the way back to you in Japan.
That is insane. That's like me being in Tokyo wanting to order sushi from the place next door, but calling my mom in Taipei to place the order
Yeah.
and having her fly to Tokyo to pick it up, fly back to Taipei to inspect it, and then fly it back to me.
We actually have a name for that. We call it tromboning because the data path looks like a slide trombone extending out and coming back.
And I imagine that just destroys your speed.
It kills the latency. I mean, the speed of light is fast, but it's not infinite. That round trip adds very noticeable lag.
Yeah.
Plus, think about the cost. You're clogging up these super expensive international backbone cables just to load a local map.
So local breakout is the fix. The diagram shows the UPF sitting in the visited network.
Correct. With local breakout, the network says, hey, I see you're in Japan. I'm not going to send this data home. I'm just going to dump your traffic onto the internet right here in Tokyo. Phone to tower to Japanese UPF to the Japanese internet.
So the data never goes home.
The data payload never goes home. It takes the shortest possible path, and that is why you get 4K video without buffering.
Okay, that makes total sense for the muscle. It's efficient.
But
But here's the problem I see. If the data never goes home, how does my carrier back in Taiwan know I'm even using it?
Yeah.
Right. I mean, if I'm just dumping data in Japan, my carrier back home can't see it. How do they bill me? How do they know I'm not just, stealing internet?
Right. And that question brings us to layer 3, the top line, the brain. Because while the muscle is working locally in Japan, the brain is having a very intense, long-distance conversation with home.
Okay, so let's look at this blue line across the top. The notes say this is an SBA, a service-based architecture. It looks like a bus.
It is a bus. And this is probably the biggest shift from 4G to 5G. In the old days, these network functions were physical boxes. If you wanted the billing machine to talk to the gateway machine, you literally had to plug a cable between them.
All hardware.
All hardware. But in 5G, these boxes, AMF, SMF, UDM, they aren't physical appliances anymore. They're software. They are microservices.
Like how modern apps like Netflix or Uber are built.
Exactly like that. They're just code running in containers, maybe on Kubernetes. And that blue line isn't a wire, it's an API bus. These services are talking to each other using things like HTTP2 and JSON.
So they're literally sending web requests to each other like, hey, can you authorize this? Sure, here's the token.
That's the idea, yeah. It makes the network incredibly flexible.
Yeah.
So let's look at the cast of characters on this bus. Who's running the show in the visited network?
Okay, looking at the left side, the first box I see is the AMF.
The Access and Mobility Management function.
That is a mouthful.
It is. Think of the AMF as the concierge at a hotel. Or maybe the bouncer at a club.
I like bouncer.
Okay, the bouncer. When your phone connects to the tower passes you to the AMF. The AMF is the gatekeeper. It says, who are you? Let me see your ID. It handles your registration, and it keeps track of where you are.
Okay, so he's checking IDs at the door. Next to it is the SMF.
The session management function.
Okay.
So if the AMF is the bouncer, the SMF is the floor manager.
The manager.
Yes, the AMF handles you, the user,
Yeah.
but the SMF handles your session, your data connection. Remember the UPF, the router we talked about.
Muscle, yeah.
The UPF is dumb. It just moves packets. It doesn't know where to send things. The SMF is the boss of the UPF. The SMF tells the UPF, hey, open a pipe for this person. Route their traffic to the internet.
So the SMF is the traffic cop.
Exactly.
Yeah.
And the SMF makes its decisions based on those two other little boxes you see there, the NSSF and the PCF.
NSSF network slice selection function.
That decides which slice of the network you get. In 5G, we can virtually slice up the network. So maybe you're a regular tourist, you get the standard slice. But maybe you're a paramedic, and you need the emergency slice that never, ever lags. The NSSF picks the right lane for you.
And the PCF.
Policy control function. That's the rule book. It checks your plan. Do you have gold status? Are you being throttled? It gives the rules to the SMF.
Okay, so that's the team in Japan, the bouncer, the manager, and the rulebook. But here's the catch. The rulebook in Japan is empty for me. I'm from Taiwan. They don't know who I am.
Exactly. The Japanese AMF looks at your ID, your SIM card, and says, I don't recognize this person. They're not in my database.
So we have to call home. We have to cross the dotted line to the right side. Who lives over there?
Two very important VIPs, the
Yep.
UDM and the AUSF.
UDM, Unified Data Management.
That's the master database. It holds everything. Your encryption keys, your data plan, your billing address. It is the source of truth for you as a subscriber.
And the AUSF.
Authentication server function.
Yeah.
It works with the UDM to perform all the complex math, the cryptography, that proves you are who you say you are.
So we have a situation. The bouncer in Japan needs to ask the master database in Taiwan if I'm allowed in. But these are two different companies. They might be competitors. I assume they don't just open up their databases to each other over the public internet.
No, that would be a catastrophic security failure.
Yeah.
If I let you query my UDM directly, you could map out my entire network, you could find my vulnerabilities, you could target my other subscribers. It would be a disaster.
So how do they talk?
Look at the very center of the diagram.
Yeah.
Right there, straddling that dotted line. You see two boxes connected by a specific interface labeled N32.
VSCPP and HSCPP.
The SCPP, Security Edge Protection Proxy.
SCPP. It sounds like a secret agent.
It kind of is. Think of the SCP as the diplomat. Or maybe the heavily armed border guard. It is the only door in or out of the control plane for roaming traffic.
So the Japanese AMF doesn't talk to the Taiwan UDM directly?
Never. The Japanese AMF talks to its local VSEPP, the visited SEP. It says, hey, I have a foreigner here. Can you check them out?
And what does the VSEP do?
It performs what we call topology hiding. It takes that message and it scrubs out all the internal IP addresses and network details. It encrypts the payload, and then it sends it over that N32 link across the ocean.
It creates a sanitized, secure diplomatic pouch.
That's a perfect way to put it. It sends it to the HSEPP, the home SEP in Taiwan. The HSEPP receives it, decrypts it, checks that it's coming from a trusted partner, and then it hands it to the UDM.
So the networks can cooperate without exposing their soft underbellies to each other.
Trust, but verify. That is the SEP's job. Without the SEP, 5G roaming basically wouldn't exist, at least not securely.
Okay, I think I have all the pieces now. We have the muscle, the UPF doing the local breakout. We have the brain, the AMF and SMF managing the traffic. And we have the diplomats, the SPP, handling the secure long-distance call.
You got it.
So, to really lock this in, I want to tell a story. Let's walk through this diagram step by step. Imagine our listener has just landed at Narita Airport. They turn off airplane mode. What happens first?
All right, the play-by-play. Step one is registration. Your phone wakes up, it sees a signal from a Japanese tower, and it basically shouts, hello, I want to connect.
And the tower catches that signal.
The tower forwards it to the local AMFR bouncer. The AMF looks at the SIM card info and sees the country code. It says, wait a minute, this isn't a Japanese user. This is a subscriber from Taiwan.
Step 2.
Step 2 is authentication. The bouncer needs to check your validity. The AMF creates a request and sends it to the VSEPP. The VSEP encrypts it and shoots it across the N32 interface to the HSEPP in Taiwan.
The diplomatic pouch flies across the ocean.
Right. The HSEPP hands it to the UDM, the master database. The UDM checks its records. Yep, this is Alice. Yes, she has a roaming plan. Yes, her bills are paid.
Just thumbs up.
The home network sends an authentication success message back through the SEPPs to the Japanese AMF. Now, you're registered. You see the bars on your phone.
But I don't have internet yet. I open YouTube to kill time in the customs line.
Okay. Step 3 is session setup. The AMF sees you want data. It calls the SMF the manager.
Yeah.
The SMF has to make a decision, so it consults the PCF, the rulebook.
And this is the critical moment for local breakout.
It is. The rulebook says, this user is roaming, but for internet traffic, we want low latency. Use local breakout.
So the SMF does not build a tunnel back to Taiwan.
Correct. The SMF reaches out to a UPF, a router, sitting right there in the Japanese network. It tells the UPF, open a pipe for this phone.
And finally, step 4.
Step 4 is data flow. Your request goes phone to tower to the Japanese UPF to the YouTube server, which is probably also in Tokyo. The video starts playing instantly.
It's amazing. And while I'm watching that video, is the blue line, the brain, still active?
Constantly. This is what people forget. While the video data flows locally, the Japanese SMF is counting the bytes.
Mm-hmm.
And every few minutes, it sends a little report via the SEPPs back to Taiwan saying, hey, Alice just used another 50 megabytes.
So my carrier in Taiwan knows what to bill me, even though they never touched the actual video data.
Exactly. It's two parallel conversations. One is, here's your video, which is local and fast. The other is, here's the bill, which is global and secure.
That separation, it's really elegant when you think about it.
It is. It's what makes 5G a true cloud-native architecture. By decoupling the control plane, the software, from the user plane, the hardware routing, you really get the best of both worlds.
You know, it's funny. When we started, I called this a bowl of alphabet soup, but now that we've walked through it, it feels more like a choreographed dance.
It is a dance of a very precise, high-speed dance between two massive organizations.
And there's one more thing the notes mentioned that I found fascinating. We talked about how these boxes, the AMF, the UDM, are just software now. They live in the cloud.
Yes, that's right.
Does that mean the home network doesn't actually have to be a physical place anymore?
That is the provocative thought I want to leave you with.
Yeah.
In the past, a telecom network was a building. It was full of copper wires and switches. But now, it's just code.
So where does this go?
Well, we're moving toward a world of ephemeral networks. Imagine a massive music festival in the desert or a disaster relief zone after a hurricane.
Yeah.
There's no infrastructure there.
None.
You could find a server rack or even just use a satellite link, and you could spin up a home network entirely in software containers right there on site.
A pop-up network.
Exactly.
Yeah.
Thousands of people could roam onto it instantly. The local breakout, the UPF, would handle all the local data needs, like emergency maps or festival apps, while the authentication happens, well, anywhere in the world.
So the distinction between the network and the cloud is basically gone.
It is blurring every single day. The diagram we decoded today shows Japan and Taiwan, but in the future, home and visited might be fluid concepts defined purely by software, spinning up and shutting down as needed.
That is a wild concept. We went from a terrifying technical diagram to the future of fluid pop-up infrastructure.
That's the power of this architecture.
Yeah.
It's not just about speed, it's about flexibility.
Well, I will definitely never look at the 5G icon on my phone the same way again. Next time you're traveling and your map loads instantly, you can give a little mental high five to the VSEPP and the local breakout.
They're working hard for you.
Thanks for diving in with us. We'll see you on the next deep dive.